Welcome to Tech Diet. Let's dive into our today's problem, maximum number of jumps to reach the last index. It says you'll be given an integer array and an integer target. We need to know whether we can reach from index 0 to the last index of the array, given we can only make the jump from index I to index j if the difference between those two elements lies within the range of targets. So let's just try to simulate this scenario. We'll have here this array. So initially I'll be at 0th index with no jumps. So can I reach from 1 to 3? I can reach. The difference is 2. It's lie within the range. So can I reach from 1 to 6? No. Can I reach from 1 to 4? No. Can I reach from 1 to 1? Yes. So then we need, okay, can I reach from 1 to 2? Yes. So I can directly reach from 1 to 2 in the single one jump, but we need to find the maximum jumps, right? So let's just keep track of each jump. So initially I can reach 0. Can I reach the corresponding 3? Yes, in one jump I can reach. I cannot reach this guy. I cannot reach 4. I can reach this in one jump. I can reach it in one jump. So then I need to know what is the maximum number of jumps I can reach at particular index, right? So if I try to say, can I reach this 0? I can reach. Can I reach this second index? Yeah. Can I reach this sixth, the third index? So I can't reach from here, but I can reach from 3, no. So that will be again -1. Can I reach this 4? I can't reach from 1. I can reach from 3, yes. How many jump I'll take? From to reach 3, I'll take one jump. To reach 4, I'll take one more. That's 2. And then can I reach this 1? From 1, I can reach 1. That is 1. From 3, I can reach 1. Yes, I can reach. That will be 2 number of jumps. From 6, no. From 4, no. That's all. So can I reach from 1 to 2? Yes. Can I reach from 3 to 2? Yes. Can I reach from 6 to 2? No. 4 to 2? Yes. 1 to 2? Yes. That will be 2, but we'll keep the maximum. So we'll land into 3. So that is the maximum number of jumps that you can reach. So yeah, you'll see this is the classic DP problem. So let's just initialize this DP with the size of our given num size, and then we'll here, so each dpi denotes the maximum number of jumps that it can make to reach that index, right? So we'll have the corresponding, let's say I'm starting with position 0. So at 0th position I don't need to make any jump, so I can reach there, no jumps. So I'll start from position 1. If position is less than the corresponding nums dot length position plus plus. So at this point I need to say what all previous indexes I have seen. So previously I have seen these many, and I need to say the dp of my position will be, it will store always the maximum that we can reach. So maximum that I can, number of jumps I'll take to reach this position, 1 plus the corresponding dp of previous indexes, whatever the maximum out of these options. One, let's say I'm trying to reach 1. So how many options I have from 1, how many options I have from 3, plus this new jump. But that should only be done if it's a feasible jump, right? So let's just write that function. If it's the feasible jump, how do we calculate the feasible jump? We'll just calculate the corresponding difference between those elements, nums of position minus nums of I, and we'll just pass the corresponding target to it. And let's pass our guy this dp of position currently, or the corresponding previous element which we're talking about. So let's just write this function. It's called is feasible. It will return a boolean. It will take a parameter called difference and the corresponding target and the corresponding previous jump, how many previous jumps it has taken. So let's look at this example 6. We know 6 was never jumped, right? So it was always -1. So I cannot resolve the corresponding 4, 1, 2 using this sixth element. So I need to make sure the previous jumps are, let's just say we can say previous jumps If this is a positive number, it should be, it should not be equal to minus 1, let's say, and my difference, okay, let's just add it to absolute difference should be less than equal to 2, or the corresponding target. As in our example it was 2, you can just say the corresponding target. um, then it's feasible jump, I'll resolve the TP at corresponding index, then we can just return the corresponding value of the last index. Return TP of nums dot length minus 1. Let's just try to run this. So missing semicolon, and it's called as nums. Okay, it should be j. We are returning 0, it's expected minus 1. Let's just cross verify. So it should be within the target. dp of j, the previous jump should not be minus 1, that is fine. And we are returning the difference, the corresponding target. Okay, so at here we are never making that corresponding position to minus 1, right? So let's just run it again. Hit submit. Yeah, it's accepted. Thank you.